Hello everyone, I'm Chad Leukes. I lecture for the Department of Physics and I'm a PhD candidate in the Department of Astronomy, both here at the University of Cape Town in South Africa. Previously, I did my undergraduate studies in physics. I also hold both honors and master's degrees in astrophysics. My research has focused on astronomy education, particularly student reasoning, and today I'll be talking a bit about this research which formed the basis of my master's dissertation. The title of my master's dissertation was Introductory Astronomy Students' Reasoning about Astrophysical Phenomena Within Their Observational Experience. Before taking a deeper dive into exactly what this research entailed, I want to first explain to you where it comes from. In other words, why I investigated student reasoning. So why investigate student reasoning? You see, astronomy education research, or AER, has largely, not exclusively, but largely focused on identifying students' so-called misconceptions. Comments describe these misconceptions as being deep-seated beliefs inconsistent with scientific understanding, and further noted that these misconceptions tend to reappear even after instruction. Here the word instruction refers to teaching or lecturing in the case of a university. Given the fact that these so-called misconceptions often reappear after instruction, I felt the need to look at this from a different angle. Instead of thinking of these misconceptions as beliefs that are difficult to change, instead I want to frame it like this. Let's think of these misconceptions as being the endpoints of student reasoning. And then, given the fact that these misconceptions are well documented in the literature, I put forward the following question in my dissertation. Shouldn't we instead first seek to understand how students think or reason about astronomy concepts before seeking to influence what they think or the outcomes of their reasoning? To investigate student reasoning, it requires that you elicit as much as possible from the students. I did this using questionnaires, but you could, for example, conduct interviews with students or hold group discussions. I combed through the literature and found no suitable questionnaires. In the literature, they are referred to as concept inventories, and essentially they test students' conceptual understanding of topics. In other words, they focus on what students think or the outcomes of student reasoning. Now, because I was interested in how students reason within the context of astronomy, I designed a new questionnaire, the ARQ, or Astronomy Reasoning Questionnaire. In designing the questionnaire, I first chose the topics that the questions would cover. Most of the topics included were informed by the IAU Big Ideas in Astronomy project. I focused on Big Idea 2. Why? Well, because the sub-ideas contained within Big Idea 2 aligned closest with the objectives of the study, namely to probe student ideas and reasoning on astronomical phenomena that they experience observationally. In total, I included 8 topics in my questionnaire. However, I will list the 4 which are analyzed as part of this dissertation. So the day-night cycle, seasons, differences between the luminosities of stars, and why stars appear to twinkle. So how did I frame the questions? Well, research by Ali and Damari found that students' writing was highly dependent on perceived audience, and students were more likely to engage in meaningful and critical thinking if their perceived audience was a friend or peer, in other words, someone who the student perceives as knowing less. Alternatively, Ali and Damari found that when the students perceived the audience as being someone who knows more, for example, if they thought that they were speaking to a lecturer or teacher, that the student was then likely to experience feelings of nervousness and fear, in which case their cognitive abilities are often diminished. So here is an example question. Why do we experience day and night every 24 hours? This is a typical question, one that most of you may have asked or been asked before, but this is not how I phrased the question. Instead, I phrased this question as follows in the questionnaire. You must give a talk to a grade 10 class about why we experience night and day every 24 hours. Write in detail what you would tell them, and you may draw diagrams to aid your explanations. Now, in this question, the university student is positioned as a knower. In other words, the student knows more. They are the proverbial expert, in comparison to the school kids that the student needs to talk to. Now, the statement, write in detail what you would tell them, you may draw diagrams to aid your explanations. This statement I included on every page with every single question. All other questions, which I'm not showing for time, were phrased similarly. I administered the questionnaire to the first year astronomy students on the first day of class at UCT, the University of Cape Town. And then, of course, because this research involves taking data from human participants, I obtained ethics approval from the university. And then the analysis followed the grounded approach, particularly the constructivist grounded theory method that was developed by the American sociologist Kathy Sharmas. Now, the first step in the analysis is to code the data. Here, the word code does not refer to the process of writing instructions for computers. No, instead it refers to the process of analyzing qualitative data. So you begin by reading a student response, identifying key phrases, which we then shorten into key ideas. And it is to those key ideas that I then assign numerical codes. I then look through all the other student responses to a question, and where that same idea is present, I assign the same code to those students. I then repeat the process, assigning new codes to new ideas as and when they arise. And then I create a tally, which in a nutshell allows me to say things like this: so many students said this, so many students said that. In this table, we see all the key ideas identified in student responses to the question on day and night. In the center column, we see the number of students who mentioned a particular key idea. And then also it emerged that many of these key ideas were similar, and so I grouped them into broad idea categories. Perhaps unsurprisingly, 95% or 39 of the 41 students mentioned Earth rotation in their answers as to why we experience night and day. More interestingly, though, 85% of the students added that the face of the Earth pointed towards the Sun experiences day, whilst the face pointed away experiences night. In other words, 85% of the students ventured further than simply stating, well, we experience day and night because the Earth rotates. In this image, I am simply showing you how the ideas were connected in forming the larger idea category, Earth rotation. Now, this image is interesting for several reasons. Firstly, if you look closely, you will see that the students express themselves diversely, and therefore we can say that they think in diverse ways. Secondly, students experienced difficulty with terminology. Many of them used the words orbit, rotate, spin, revolve interchangeably. Now, ordinarily in a test setting, they might be marked wrong. But because they were encouraged to write as much as they could, you could see that they knew what they were trying to explain, even when their vocabulary wasn't correct. One of the other questions I asked the students was to explain why stars appear to twinkle. Now, twinkling is not taught in school, and this was the first day of class, so what they said is likely to be their own ideas. Again, many ideas were identified in the student responses, and I was able to group similar ideas into larger idea categories. So here's an example. 20% of students explain twinkling in terms of the energy generation in stars, and you can even track a reasoning chain here. So some students said that these chemical reactions in stars produce light, and fluctuations in these chemical reactions causes fluctuation in the light intensity. This in turn we then perceive as twinkling. Here is another category of idea which emerged in the student explanations on why stars twinkle. So 20% of students explain twinkling in terms of interferences along the line of sight. For example, some students say that light from stars is a constant stream, and that there's gas and dust that passes between the star and us, thereby blocking the light and interfering with the light, which in turn we perceive as twinkling. So why do stars actually twinkle? Well, It's due to Earth's atmosphere. Earth's atmosphere is windy, it's turbulent, and so it has a tendency to refract light from faraway objects like stars. Sadly, only one student was able to offer the correct explanation to this question, but there's a bit more to it than this. So, what was more interesting was that the students provided rich, detailed explanations, and this revealed a depth of thought and engagement. Of course, this is often masked by multiple choice questionnaires. And although many of the students failed to produce correct explanations to concepts they had not yet been taught, most of our students offered well-reasoned, plausible explanations. You see, they engaged in logical sense-making. So in conclusion, reasoning is the hallmark of scientific thinking, and I encourage you to foster spaces where you encourage this. When students are wrong, probe why. Simply stating they are wrong may diminish their ability to reason. You see, when you don't say why they are wrong, they may conclude that their reasoning is flawed, where in actuality they may have engaged in sound, sequential logical reasoning, however based on incorrect starting ideas. So, praise the ability to reason, but probe the origins of the ideas when the explanations don't align with yours. Thank you for listening. I'm of course more than happy to take any questions, and you are more than welcome to email me on the address provided.